All right, so in this video, we're going to be walking through how to do linear regression in linear algebra. Now, this regression equation that we do in this process that we follow in linear algebra is readily generalizable to any other kinds of regression as long as you have unknown coefficients multiplied by a variable or an expression that can be evaluated. We can always find the coefficients for the equation. Now, after we do this example with the linear equation, we'll do the same example with one other equation just to kind of see how the process is similar or different. But in linear algebra, there's this formula called the normal equation. And we're going to walk through how we derive this as we go through the example. But this is the equation that we're going to try to solve. And the basic idea here, this is somewhat further into linear algebra than sort of entry level. This is not necessarily always covered in a one semester introductory linear algebra course. But basically, what we're trying to do is we have this four-dimensional problem with 4 points, and we're trying to simplify it so that it can be expressed as best as possible with only 2 dimensions. So our beta 0 and our beta 1. Now, if we had 4 points in 4 dimensions, we could get a plane that goes through all 4 points perfectly. That would be fine. But a hyperplane. But we don't have 4 dimensions. We only have beta 0 and beta 1. And so what we're essentially doing is we're projecting our 4-dimensional problem onto a 2-dimensional subspace. And so there's a whole machinery of theory about how we do that, which is how we derive our normal equation in the first place. Now, we're going to work on this from the perspective of the mechanics of doing it and not from justifying the theory. If you're interested in the theory, there are books out there. I'm sure there are videos out there to explain how this projection onto a subspace works. But again, the purpose here is to walk through how you would do the computation of the linear regression equation. And I will have to tell you that this process, it will give you exactly the same kind of answers that you get out of your calculator. And there is a calculus way of actually deriving these equations as well. It's possible I may do them in some other video at some point. But the calculus process and the linear algebra process actually very interestingly give you also exactly the same answer. And this process is a little less computationally nasty. And one of the things I like about it is, again, it's completely generalizable to other kinds of equations under certain circumstances. Whereas some of our other processes, if you're doing like a calculus-based approach and you want to do a quadratic regression or something like that, you have to change all your formulas. And those are all covered. All those formula changes are actually accounted for just by our matrix multiplication, which I think is really nice. All right, so these are the points that we would like to plot a regression line for. And so just to see what these points look like, we can plot them. I did this in Desmos, and it comes in a little big, but we can see we have our points here. They're kind of on a straight line, but not exactly on a straight line. And we would like to come up with a line that fits as closely as possible to our points. That's the fundamental idea behind linear regression. Now, the way that we're going to approach this from an algebra expression, a linear algebra approach, is we're going to start with the linear equation that we want to estimate, and we're going to start putting in our points for the system that we're trying to solve. So we'll have y on one side of the equation and our constants on the other. To be consistent with our linear algebra approach, we're going to put the y on the right side instead of the left side. So this will become b sub 0, which we don't know, plus b1 times 1 for x is equal to 6. And then b sub 0 plus B1 times 3 is equal to 9. Now we could get an exact solution if we could stop here, but instead we are over specifying equals 11 and B0 plus B1 7 is equal to 18. Now, if only we had a way to transform this into a solvable problem. Well, it turns out that we do. So the first thing we're going to do is actually we're going to construct our matrices. We're going to have a matrix, make a nice square bracket. And what we're going to have is we're going to have essentially a 4x4 or 4x2 matrix. So it has two columns of coefficients, but it's going to have, so I'm going to start with a 3x3 and then we'll just make this a little longer. So now the coefficients for B0 go in the first column. So 1, 1, 1. And then the coefficients for B1 are going to go in the second column. And let's see, make that like so. There we go, 1 and 1. And then in our second column, those are going to be the coefficients for B1. So those will be essentially the x values, 1, 3, 4, 7. And then we will have a vector of our coefficients. So B0 and B1. And that's going to be equal to our vector of our y values. So 6, 9, 11, and 18. And essentially, the labels that we're going to put on our equation is that our first matrix, our coefficient matrix, is A. Then we're going to have our B matrix, which represents our coefficients, B1, B0, B1, and then that's equal to Y. Now, as we've said, unless these equations line up on a straight line perfectly, there's no way to solve this. It's overspecified. But when we want to make a projection onto a two-dimensional subspace, we can force it to be solvable, again, with our best approximation. And the trick is going to be to multiply both sides of our equation by A transpose. Now, what that will have the effect of doing is if we multiply a 4x2 matrix by a 2x4 matrix is on the left side, we're going to get a 2x2 matrix that will be square. And then we'll have something that will be dimensionally capable of being solved for two coefficients. Now, again, the theory behind this projection strategy is, I'll leave to another analysis, but this is essentially what we get. And you can actually see, if you think about it, you can see that it's going to work out dimensionally. Multiplying a 2x4 by a 4x2 gives you a 2x2 matrix. And so A transpose A is going to be a square matrix. And A transpose Y is still just going to be a vector, but it's going to be a 2x1 vector instead of a 4x1 vector. So again, we've now, at least dimensionally, we can justify saying, okay, at least this is now probably solvable. The question will be, is A transpose A solvable? Is it going to give me a unique solution, or is it going to be dependent? The main condition that we have here is that the columns of our original A matrix have to themselves be independent. And if they are, then the columns of our A transpose A will also be independent. And then we'll be able to solve it for an exact solution. Now, there are strategies in linear algebra, which are beyond the scope of this video, to handle the situation where A transpose A is in fact not invertible. so that you can still come up with some sort of solution, even if it's not a unique solution. However, we're not going to handle that in this case. We're just going to work with the assumption that is usually true in most linear algebra problems, which is that the columns of our vectors, columns of the A matrix, are in fact independent. You can see there's only two of them here. They're not multiples of each other. It's clearly going to be fine for this problem. And this, from this point, is how we actually derive the normal equation, because now what we're going to do is we're going to solve for B by multiplying by A transpose A inverse. And again, we have to multiply by A transpose A to make it square. And then collectively, we can invert that result, A transpose Y. And then our B vector will be our coefficient vector for our B0, B1. Now, for this particular problem, therefore, what we're going to have to do is we're going to multiply on both sides of this matrix by A transpose. So let us find a bracket and our rows are going to become columns, and our columns are going to become rows. Spread that out a little bit so that we can read it. And then same thing on this side of the equation. And then we can do the multiplication, and we'll end up with the following, again, 2 by 2 matrix. And so when we multiply A transpose times A, we end up with the matrix 4, 15, 15, and 75. And when we multiply A transpose times our Y vector, we end up with 44 and 203. And then we can go ahead and again, we could either row reduce this if we wanted to as an augmented matrix, or we can multiply by the inverse. So if we multiply by the inverse, we're going to end up with essentially this equation. And the inverse is going to end up being -1 and -1/5 and -1/5 and 4/75. And then when we go ahead and multiply that times our A transpose Y, we'll get our coefficients. Now, in some cases, for small problems like this, you may be able to convert them to fractions. And so I'll give the fraction version for this example since it's possible. However, particularly for bigger problems, you're not really going to be able to do that. You're just going to get decimals, particularly if you're working in like a TI or something. It can handle certain kinds of coefficients, but at certain kinds of denominators. But then up to a certain point, it will say, yeah, no, I don't want to do that anymore. 2027. So these are our coefficients. Now, what do we do with these coefficients? Well, what this is saying is that our equation of the line of best fit, the first coordinate is our constant, and the second coordinate is our coefficient of x. Now, if we go back to, let's say, a graphing program and we try to plot this through our points, we can see whether or not this actually does what we expect it to do. And what we get when we plot this, again, let's shrink this so we can actually see it on the whole screen. What we get is here is our original points that we're trying to make a line of best fit for. And in fact, we see that, yes, this does seem to be a pretty good fit to the line. We would need, again, more theory to justify that this is actually the line of best fit, but it is. And again, all of our processes, be they calculus or our linear algebra machinery for, projection of best fit and things like that, those all indicate that this is the line of best fit, and they all give us the same result. Now, if I wanted to extend this, as I said, to not a nonlinear example, to not a linear equation, but maybe I wanted to extend this to a quadratic model. So maybe y equals b sub 0 plus b1 x plus b2 x squared. I can use exactly the same procedure. My linear equations would no longer be linear because I would have a third coefficient in them, and that would be b2 and my x variable squared. So that'd be 1 and b2 times my x variable squared, and b2, oops, that wasn't what I wanted, plus b2 times my x variable squared, and then b2 times my x variable squared. And so I would end up with a matrix with 3 columns. And 4 rows. And so this would be 1s all the way down, but then I would have my x values in the second column, 1, 3, 4, 7, and then I would have in the third column, I would have all the squares. So 1, 9, 16, 49. But the rest of my equation would otherwise be the same. But again, this is still too many equations to solve for, actually, I would need a third component here. There we go, not b squared, b sub 2. So I would have 4 equations and 3 unknowns, so overspecified still. And as long as I have fewer coefficients to specify than I have functions, then I can do, basically a projection onto a subspace to get the line of best fit, or in this case, the quadratic function of the best fit. But my procedure would otherwise be identical. I would multiply by the transpose of this matrix on both sides of the equation, and I would proceed then just exactly as I had before. I would have a 3 by 3 matrix to find the inverse of, but the inverse for 3 by 3 matrices is computationally difficult for people, but very straightforward for a calculator. And so generally, as long as you're not solving for an equation that has, 50 coefficients in it, I mean, this is an algebra process that you can do in your TI. So it is not that difficult to do. And so computationally, this is a very efficient approach to finding a linear regression or any other kind of regression model, as long as you can separate out your variables and your coefficients. Now, basically, this process will work for almost any kind of function, as long as the coefficient is multiplying on the outside. Where this will fail is if you have a coefficient that's on the inside of the expression. So if you were trying to do sine of, so A is an unknown, sine, and then on the inside of your sine function, you had bx plus c or something like that. That would fail because it's inside the sine function. That's not a linear relationship after you substitute your values. Now, if you knew what the period was, for instance, or you knew what the phase shift was, and you could guess at those and put those into your equation, then you would have all constants inside your sine function. You could evaluate the sine function, and then you could do your solve for your coefficients on the outside. But some kinds of problems, you will have to do transformations on them. So like e to the ax, a in the exponent is bad, but if you do a log on both sides, then you can have the log on your y side. Log of a constant is a constant, and then you're just have your coefficient times x on the x side. And so again, you can do that without too much difficulty. So there are models that we call intrinsically linear, power functions, log expressions, reciprocal functions, exponential functions. Those all can be turned into just straightforward linear problems with just transforming one or both variables. But quadratic models also can work like this. It's just like trig functions, if you have coefficients on the inside, are not going to work. And so you would need another kind of process for that. But if the coefficients are only on the outside, again, if you know, or you can at least make a really good guess for the period and the phase shift, then you can still do this for the outside coefficients. How big is the amplitude? How big is the vertical shift on your function? You can still do that for this kind of a process. But again, you would need your coefficients times a constant on the outside, no coefficients left inside your functions. But then you can use this process to solve for any of these kinds of equations. Again, linearity in the coefficients, not necessarily linearity of function.